If you notice your homework assignments, they cover 4.2, 4.3, 4.4, and 4.6, and so there's no 4.5 here. 4.5 is, the methods in 4.5 is a different method of being able to accomplish the same thing that we're accomplishing in 4.4. So 4.4 is methods of undetermined coefficient, and it's summarized as the superposition approach, and 4.5 is using the annihilator method. So both of these allow you to solve for higher order linear DE with constant coefficients. Non-homogeneous. But only for special functions. And the special functions are, you know, the polynomials, the exponential functions, and the sine and cosine. And combinations of those things. If you were to multiply the polynomial with an exponential function, then we have those special approaches. So since they cover the same thing, I think it might be neat to look over the annihilator method if you want to do that on your own. And the video that was playing before class started was an example of the annihilator method, which we could have solved for using the superposition approach. And so if you want to mess around with that, feel free to do so. But I'm going to just focus on 4.4, and in fact today we're going to quickly wrap it up and jump into 4.5. And 4.5 is going to allow us to solve for non-homogeneous differential equations that would have functions that are a little bit more complicated than this. So the homework, I think, is due sometime soon. This one, 4.2, should have been done already. 4.3 and 4.4 were the last couple of things that we ended off with last week. Are you guys having any issues with 4.3 or 4.4? Should we do one or two homework assignments from there? Which ones? 4.3 or 4.4? 4.3? One from each. So we have 10 problems here. Do you guys know what the problems are off the top of your head? 8. All right, let's do number 8 from 4.3, and then we'll pick a problem from 4.4. So this is a third order differential equations with initial conditions, and if it's a third order differential equation, we should have 3 unknowns, and with 3 unknowns we're going to need 3 initial conditions to help us solve for that, and these are the 3 initial conditions, it looks like. This is a homogeneous differential equation with constant coefficients. It's linear. So all we have to do is solve for its corresponding, what do you call it, something or other, auxiliary equation. So let's jump to the auxiliary equation, and we'll use m to the third plus 4m squared plus 4m. And there's no other term here with a y, so there's no constant term, and we'll set that equal to 0. And if we have one of these things where we can factor out an m, that's good. We want to try to factor as much as we can. And then we have m squared plus 4m plus 4, which we can also factor, right? M plus 2 squared. And so we're going to have 2 with multiplicity of 2, or negative 2 has multiplicity 2. So if we write down our solutions for our auxiliary equation, we've got m is equal to 0. And we have m is equal to negative 2 with multiplicity 2. So with m is equal to 0, we're going to get our solution y is equal to e to the 0 times x. Well, that's just 1, right? So is 1 a valid solution for this, a constant? Yeah, maybe. Well, let's see how that works out. M is equal to negative 2. We got y is equal to e to the negative 2x is a solution. But it has multiplicity 2, so we should expect another one out of this. So our third, I guess we should label this y1, y2, y3. Our third, what's it called? Fundamental solution. We know we have multiplicity, we just tack on an extra x in there. So x e to the negative 2x. So it looks like our y is going to equal to c1 times 1 plus c2 times e to the negative 2x plus c3 e to the negative, x times e to the negative 2x. Okay. Now we are going to use our initial conditions to work this out, to help us solve for this. So it looks like we're going to need y of 0 is equal to 0, y prime of 0, and y double prime. So let's find y prime and y double prime. Y prime is negative 2c2 e to the negative 2x plus c3, and then I have to use a product rule, e to the negative 2x minus 2x e to the negative 2x. And usually if you're like in Calc 1, you take the derivative, you don't have to simplify it, but since we have to do a little bit more work here, we got to take the derivative again. It might be worth simplifying. So I think I can group together the e to the x's. So that's minus 2c2 plus c3 e to the negative 2x minus 2c3x e to the negative 2x. Hope I did that right. Maybe a parentheses around there, yeah. Okay, and then we need to take one more derivative. Y double prime is equal to y double prime is equal to, let's see. So this whole thing is a constant. We'll throw another -2 out there. -2 c2 plus c3 e to the -2x minus, I'm going to need more space here, 2c3. And then the derivative of this thing, which is what we found earlier, e to the -2x minus 2x e to the -2x. And then we could try to simplify this a little bit more, but I think I'll just stop here and then we'll plug in the points and plug in the initial conditions and see what we get. All right, let's use the first initial condition, which is y of 0 is equal to 0. This is going to get us the first, or the original y, and you put 0 in for x. Well, if I put 0 in for x, I think the only thing I'm going to get rid of is c3. So I got c1 plus c2 times 1 is equal to 0. Now the first derivative evaluated at 0, we'll get rid of the second term, and I will just keep minus 2c2 plus c3 equal to 1. And then second derivative, y double prime of 0 is equal to -9. We go to y double prime. Let me just multiply this out, and I'm going to put 0 in for x, and that's only going to get rid of one term here. So I'll have two terms for the first term, and then I'll have this term. But I'll multiply this out just so make it a little bit easier. I got 4c2 minus 2c3. And then I'll have minus 2c3 equal to -9. Let's see if we can get this written a little bit better. c1 plus c2 equals 0. -2c2 plus c3 equal 1. And positive 4c2 minus 4c3 equals -9. Did I do that right? So we solve for c1, c2, c3. Can I just use a matrix for this? And can I just punch it in the calculator? So the matrix that I would probably be looking at would be 1, 1, 0, 0, 0, minus 2, 1, 1, 0, 4, -4, -9. And if I row reduce this matrix, hopefully I'll get a nice solution. Zero, 4, minus 4, minus 9. So, using Wolfram alpha, we have this row reduce thing, and I get these numbers. So, if those are my numbers, then my values would be C1 is going to equal to negative 5/4, C2 is going to equal to positive 5/4, and C3 is going to equal to 7/2. So my final answer should be, I hope, C1 plus C2 times e to the negative 2x plus C3 times x e to the negative 2x. Okay, so any way you can solve for a 3 equations and 3 unknown linear system, whether you do it by hand or do it using matrices or just plugging it into a computer, hopefully we get the same answers. And hopefully this is correct. Let's see. Let's see, negative 5/4 plus 5/4 e to the negative 2x plus 7/2 x times e to the negative 2x. Okay, looks like we got a little check mark next to it. So it must be okay. All right, any questions about the process? Find your fundamental solutions, line them all up with C1, C2, C3, or however many there are. Use the initial conditions to solve for those parameters, and then put it back. Put the values for C1, C2, and C3. Okay, let's do another one from 4 this time. The new stuff. By the way, we're about due for a quiz, so I'm going to give you guys a quiz on some of these things on Thursday. Okay. Okay. All right, well, we'll work something out if you're not going to be here. What? So, yeah, we'll still do it on Thursday. What were we going to do? Oh. Section 4.4. Number what? Really? All right, we got another third order differential equation with this time it's non-homogeneous and it has initial conditions like last time. So let's see if we can solve for this. The first thing we need is we need the solution to the homogeneous counterpart of this differential equation. And I don't know if I should write, I'll write it over again. So the homogeneous differential equation is the y triple prime plus 2y double prime plus y prime is equal to 0. And first, we do our solutions like we've done before, where we just we solve for the auxiliary equation, and then we come up with solutions for this. So let's see how this is going to turn out. I think we got, it's going to be very similar to what we had earlier, right? Y to the m to the third minus 2m squared plus m is equal to 0. So we have m squared minus 2 plus m, or 2m plus 1. Yeah. So m minus 1 squared, which is which will have multiplicity 2. And so we have m is equal to 0, m is equal to 1. So our solutions here would be y1 is equal to e to the 0x, and y2 is equal to e to the x, and then y3 is equal to x e to the x. So now we need to find a particular solution. And our particular solution should mimic what's here. What? I'll have A. Now, this is a little trickier because our particular solution should be, you should think about our particular solution to look something like this. It'll be A plus, I'm going to erase this, by the way. A plus B e to the x plus c e to the 5x. So initially, this is what I would be looking at as my particular solution. But what's the problem? Is this a problem? Is this a problem? Is that, how should I phrase my question? Should we go on? Is this okay? What? Is there an issue? What's the issue?
When I tried to work it out, it
Didn't work? Okay. Were you the one that asked for this problem? Bonnie? Oh, it's okay. I underlined a couple of terms here that raise some flags for me. And why did I underline those two terms, and what's the relationship, and what do you think we should do about it? What? Add an x. They're similar to y1 and y2. Did you see that? So they're similar to y1 and y2. So the idea here is, I can't really remember what to do. One idea is that a plus b e to the x would just merge with the y1 and y2 solutions. And if that's the case, then that's easy. Then we just go about this yp by solving for c. But I can't remember if we need to just add an x. That's my problem. Let's try it this way, and if it's not correct, then it'll be a waste of time. So the fact that these two are really just part of your solutions to the homogeneous equation means that we don't need to deal with that. We don't need to mess with that. And if a, whatever we get for a, if we get a is equal to 5, that will just kind of merge in with the y1 when we plug in our initial conditions. And same thing with b. If b was equal to 5, this will merge in with a c2 when we come up with our initial conditions. So let's maybe assume that this is going to be the case, and let's see what happens. So a particular solution then would just be e to the c times 5x. And then we need 3 derivatives. 5ce to the 5x. Y double prime is 5 squared. Ce to the 5x. Y triple prime is 5 cubed. Ce to the 5x. So we'll put into this differential equation to solve for this unknown coefficient. We have 5 cubed, that's 125, I think. Well, we'll keep it like that for now. C e to the 5x. Yeah. Well, let me write this down and we'll factor it all out. 2c 2 5 squared. Oops. ce to the 5x plus the first derivative 5ce to the 5x Oh, we do have a problem. What? Because then, yeah, this will never be equal to 2 and 24. I knew it wasn't going to be that easy. What? Shoot. All right, let me double check. Make sure. What? Yeah, with a b. Like, just keep this here, keep the a and the b. Yeah. Well, that was the other thing, but that would make this a little bit more difficult. I was trying to see if I needed to do that. Let me just check the book real quick, because there's an issue if the particular solution has parts of the homogeneous solution. Polynomial exponents, e to it's already present in YC. This means that e to the x is a solution, and the constant multiple is substituted differential equation. This produces 0. So y particular you should tack on an extra x, and then yeah, so we got to tack on an extra x. Crap. All right, sorry. This is going to be longer than what it seems. So I underlined these functions because they're an issue. They actually match up with our conditions here. So what we can do is change this to be a times x plus b x e to the x plus c e to the 5x. Oh, so y3 has an issue here too if we kept that. So let's just throw another x in there, so make it x squared.
What happened?
So what I did was for the first issue, I have a plus b e to the x. A is a constant, which matches with y1, and b e to the x matches with y2. And so I decided to put an x in front of both of those. In doing so, I put an x for this one, and I have b x e to the x. But that matches with y3. So I'm going to put another. So there was an intermediate step here, b x e to the x. But that's not going to work because my y3 is x e to the x. And you don't want, those two functions are linearly dependent, and you're not going to want that. So this is your yp. And with this, you're going to try to solve for a, b, and c.
Wait, did you just add x?
Yeah, just add x. And when we say add x, we're saying add x. We're not saying plus x, right? We're adding an x as a factor, so it'll be a factor of x. So this would be your yp, which is going to make our derivatives really complicated because of some product rules and stuff. All right, let's find derivatives. Yp prime is going to leave us with a plus, now here's where the derivative business starts. 2x times b times e to the x, derivative of the first times the second, plus the first times the derivative of the second, plus 5c e to the 5x. Second derivative, the a disappears, but now I have two product rules. So I'll say 2bx, the derivative of the first is 2b times the second plus the first times derivative of the second, plus another product rule here, derivative of the first times the second plus the first times the derivative of the second plus 5 squared c e to the 5x. Now it might be worth it to, we can only combine two things. It might be worth it to combine these two things. That would be 4bx e to the x so the third derivative is what we need. The third derivative is, okay, the derivative of the first, oh, this is just a constant, so 2b e to the x. So now we have a product rule here. I got derivative of the first times the second plus the first times the derivative of the second. And then another product rule, derivative of the first times the second plus the first times the derivative of the second. And then the derivative here is 5 cubed c e to the 5x. Wow. So, we'll 5 cubed c e to the 5x. All right, so now we put it into this equation. So the y triple prime is going to be this big mess. Let me see if I can write this down and simplify at the same time. These two, and then that's it. So I'll say 6b e to the x plus 6bx e to the x plus b x squared e to the x plus 5 cubed c e to the 5x for starters. So that's y prime minus 2 times, or that's y triple prime minus 2 times y double prime. Oh, I'm going to need more space. So the second derivative is here. I got 2b e to the x plus 4bx e to the x plus b x squared e to the x plus 5 squared c e to the 5x. And then y prime is a plus 2x b to the x, b times e to the x plus b x squared e to the x plus 5 c e to the 5x. This is going to be equal to this thing. So what I'm going to try to do is I'm going to see if I can simplify all that mess. Anything with just a plain e to the x is what I want to collect. see if we can collect some other stuff. I'm going to collect the bx squared e to the x. I got one of them here, I got -2 of them here, and I got one more here. You see how that disappeared? So let's cross those out. Now I want to collect the ones with an x e to the x. X e to the x. And x e to the x. So I got 6 here, I got -8 here, and I got 2 more here. That goes away too. Okay, now this first one didn't have a plain e to the x, did it? Nope. So now I got the terms with an e to the x here. And that would be 6b minus 4. So it's 2b e to the x. Is that correct? I also have one constant a sitting out there. All right, now the only things I need to catch are these things. So let's see what this turns out to be. This is 125, right? 5 times 5 times 5. 125. This is 25 times 2 with a negative, and then this is 5. So what does that all turn out to be? 125 minus 80? Positive, right? 80 c e to the 5x. Okay, that wasn't too bad. Oh, 80. So that wasn't too bad, and we get the right-hand side of the non-homogeneous differential equation. That gives us a value of 2 for A, and then like 12 or something, minus 24 e to the x, and 40 e to the 5x. Yeah, and so we should figure out what A, B, and C is. So A is equal to 2, B is equal to -12, C is equal to 2. 80 and 40? 1/2. Right? 1/2? Okay, so we got our particular solution. Our particular solution is ax plus bx squared e to the x plus c times blah, blah, blah. So y sub p is equal to 2x plus, or let's call it a minus, 12x squared e to the x plus 1/2 e to the 5x. All right, we're halfway there. And now we string up our solutions with constants. So I'm going to need a new page for this. So we got y1, y2, and y3 here, right? So let's call this y, your general solution. y is equal to C1 unknown constant plus C2 unknown e to the x plus C3 unknown e to the 5x. So these are your unknown values. And then we have the particular solution that we just found, which is, do I know it off the top of my head, 2x minus 12x squared e to the x plus 1/2 e to the 5x. So that's our general solution. We then go back. Yeah. Oh, x e to the 5x, thank you. Wait. Oh, yeah. Sorry. I don't know where that came from. X e to the x. So we need to take this and take the derivative 2 times and then plug zeros in and see what you get. Can I just leave it like that and then you guys can figure it out? If you want, I'll just plug it into Mathematica and see. So y of x, I don't know. C1 plus C2 times e to the x plus C3 x e to the x plus 2x minus 12x squared e to the x plus 1/2 e to the 5x. So that's my function. I could take the derivatives and then solve for this, but I'm just going to go directly to solving for this. Solve, and I'll have 3 equations. That's y of 0 is equal to 1/2. I got y prime of 0 is equal to 5/2, and y double prime of 0 is equal to negative 5/2. And each of those y prime, y double prime, and y all have C1 and C2 and C3. So I'm solving for C1, C2, C3. So I got 13, negative 13, and 11. So my general solution, or I call it particular solution, my answer should be 13 minus 13 e to the x plus 11 x e to the x plus all this other stuff. So hopefully that's the correct answer. I suppose I can check. So we got 13 minus 13 e to the x plus 11 x times e to the x. What was the rest? Plus 2x minus 12 x squared e to the x plus 1/2 e to the 5x. Okay. What? Yeah. Yeah. There's a lot of room for error. But just don't make any mistakes and you'll be fine. Okay. All right, so you got the idea. We got the idea for the superposition principle and trying to find those coefficients, undetermined coefficients, solving for them. And the tricky parts, conceptually tricky parts. Now there's, the calculation parts are tricky in general. But the conceptually tricky parts is the stuff that we ran into where your right-hand side in a non-homogeneous differential equation matches with one of your fundamental solutions to the homogeneous part. So we got a constant here, and that matches with our y1 constant. We have e to the x here that matches with our e to the x constant. And then so when we try just throwing in an extra factor of x, that fixes our constant term a to a times x. But the b e to the x became a bx e to the x, which again is an issue. And so we throw in another x to that, another factor of x to make sure that none of your fundamental solutions is linearly dependent with any of the portions of your right-hand side. So that's the big lesson there. Good luck trying to read through this. Okay, so our, it looks like the only thing that's going to change is the numerator for your second function. So your a, b, and c will be all the same. Boy, we have 10 minutes to get through another crazy method. These methods are not getting easier, right? Because the differential equations that we're dealing with are getting more and more difficult. We started with the homogeneous part, a homogeneous differential equation, and we got auxiliary equations. We found fundamental solutions, and so that wasn't too bad. And then now we make it non-homogeneous. But our restriction to the non-homogeneous is that we're kind of restricted to nice functions like polynomials, exponentials, and sine and cosine functions. And then so we do methods of undetermined coefficients, and so that got a little bit more difficult. And now we're going to try to tackle an idea where what if your right-hand side was not any of these easy functions, like a tangent or a 1 over x or something else, then what are we going to do? So that's where we are right now. And so those things we're starting to build up in difficulty, and it's just going to get harder. This has an explanation in the process in the book that comes up with these formulas. And instead of going through that, I think I'm just going to go through the process without the background explanation to that. And you guys can just read through the book to figure out the background explanation. And what we'll do is we'll do this for a g of x, a right-hand side of the non-homogeneous, with something that we already know, and we'll see if it'll work out nicely for us. But here's the process. We're solving for this type of differential equation. We're going to stick with constant coefficients. But our function here may be that easy polynomial or exponential function or something like that, or it may be a lot more difficult. So what we're going to do is first we're going to find, like we've done before, we're going to find the fundamental solutions, and then we're going to have, I guess they're calling it a complementary solution to the homogeneous differential equation. So that part we already know. And then what we're going to do is we're going to bring back the Wronskian, and then we're going to find a couple of other solutions that would work for this. So we're going to find a Wronskian of those two fundamental solutions that we got, the y1 and the y2 that we would have gotten from this differential equation. And then we're going to call that w, so we're going to use that function. And now we're going to come back with another. First we're going to solve another differential equation. Wait, where does that one come from? Standard form. Oh yeah, we're just gonna get the right hand side of the function. So they wrote it like this, thinking that your second order differential equation might be written a different way. But what we're going to do is we're going to grab this function f of x, basically the right-hand side. And then we're going to change one of the columns for the Wronskian, the original Wronskian that we had, and we're going to come up with two other Wronskian results where we're going to use this function. We're going to use 0 in that function in the first column for w1, and for w2 we're going to use 0 in that function for the second column. And then we're going to compute the Wronskian again. So we're going to come up with two functions, u1 and u2, or u1 prime and u2 prime. That's going to be the ratio of those Wronskians over the first Wronskian that we found. And then we're going to integrate to get the original u1 and u2. And then we're going to take those functions and multiply it by the fundamental solutions. And then that's going to be our particular solution. Well, that other one, the first one that we took, it took us like 15 minutes. So this one would take 15 minutes.
Is this only for second order?
This would technically work for any order. If we have a third order, then your Wronskian would be a 3 by 3 matrix. So what I think we should do is do something that's that we already know the solution to. The last one is a third order. We're not going to touch that one. So let's see how this is going to work. Let's see. Example. Let's say y double prime minus y is equal to y double prime minus y prime is equal to x. Now we can find the solution to this, or general solution to this differential equation, using what we know already, because the right-hand side is a nice function, right? So let's, I think we could do this quickly. We got the auxiliary equation, m squared minus m is equal to 0. We got m minus 1. And so we got m is equal to 0 and m is equal to 1. So our y1 is going to be just a constant. And your y2 is going to be e to the x. And so right now our solution is C1 plus C2 e to the x. See, we're done. Like, took 45 seconds. Well, oh, we're not done. We have to find a particular solution. Yp is going to be ax plus b. Yp prime is going to be ax, oops, a. And yp double prime is equal to 0. So when we plug it into the equation, we got 0 minus a is equal to x. Wait, that's not going to work. Now let's add another x in there. Follows, fails, add another x. Yeah, because 0, you got that constant. So 2ax plus b, and then this is just a, 2a. All right, so 2a minus 2ax plus b is equal to x. To a x negative plus 2a plus b is equal to x. So negative 2a is equal to 1. 2a plus b is equal to 0. So a is equal to negative a half. Minus b? Yes. And b is equal to 1? Negative 1. So y particular is going to be negative 1/2 x squared minus x. So we string these two together and we get our answer. Right? All right, so this is the old way of doing it. I guess it took more than 45 seconds. So now if we're going to do it using the Wronskian and using the variation of parameters, what? Well, this is something, this is using, this is the homogeneous part, and then we use variation of undetermined coefficients here using superposition. And so this would be, we have our answer already for this problem. What we're going to do now is we're going to do this problem using the variation of parameters and see if we're going to get the same answer. And we're out of time, so we'll have to do that next time. Okay, so next time what you should expect is that when you come into class, we'll take a quiz. Actually, I think I'll just have you guys do the quiz online. So you guys will do a quiz online, and then so we don't have to spend time in class doing the quiz. All right, see you guys next time.